Good afternoon, everyone. So, as Karin said, I am Leni Goff from Edinburgh University, where I work as a lecturer. I would like to thank Karin and Gus to invite me to do this talk here and to talk about the project Autonomous Robot Evolution, which I had the pleasure to work on for 3 years and collaborate with Gus on this project. So the presentation of Gus is very complementary with this presentation right now, because I will give you some more details on this project. It was a project funded by EPSRC, the research agency in UK, in collaboration with the University of York, the Bristol Robotic Lab, the Bio-Inspired Robotic Lab, the group of Gus and Karin, and my own university in Napier. So, as Gus explained, the big long-term vision of this project was to move evolution of robots in the hardware, in the physical realm, to do the whole evolution, optimization of the body plan and the morphology of the robot directly in hardware. Okay, so spoiler alert, we didn't achieve it within this project, but we did some significant work towards this. So I will talk in details about different aspects of the project. So how do we do the morphoevolution? The morphoevolution, I talk about morphoevolution when we use evolution algorithm to optimize the design or the body plan of the robot. And you can have a lot of weird looking robots from this and sometimes some useful ones. The robot fabricator, so how did we automate the construction of robots? Because if you want to be able to do physical evolution, you need to be able to automate the construction. Learning, of course, you want your robots to be able to do things. And finally, transferring robot from simulation to reality. So I won't talk about this part in this talk because of time constraint, but we also study this aspect. So what our robots looks like exactly? So we wanted in this project to have a very large morphological space where we could build a large different type of robots, from legged robot to wheeled robot, mixture of legged and wheels, to be able to put sensors a bit wherever we want. And also we had a motivation to move away from the modular robotic hardware, which is the most used in evolutionary robotics. So here our robots are composed of 5 pre-designed components, and they are fixed on a chassis which is freeform and voxel-based in simulation. So we have a head where you have the central computing unit, where you have the computer of the robot. You can see it as the brain, the physical brain. We have joints where we can form limbs with it. So the red bits on the robot you can see are limbs with 2 degrees of freedom form of joints. We can have wheels, we can have sensors. So the sensors are composed of, each sensors have 2 sensors, a passive infrared receiver and a proximity sensor. And the last component is just a caster wheel, is a passive wheel that evolution can put to stabilize the robot. So here you have several examples. You can see that we can have quite a large different kind of robots. And one of the very important principles of this project is that everything we do in simulation, we should be able to do it in hardware. So to be able to follow this principle is actually we design first all the components in hardware, and then we match the simulation to the hardware. So here you see all the components I've presented before in hardware and some example of robots here. For the skeletons, or what we call the skeletons, the chassis, we 3D print it. Okay. All right. So the question here is, how do we move from this simulated robot here to his physical twin, like Gus like to call them? So these 2 twins. We are using the robot fabricator. So the robot fabricator was designed and conceived in the robotic Bristol Robotic Lab. And here you see a video of the final version, which is still used in York, in the University of York. So here is composed of 2 3D printers to print the skeleton, a robotic arm to assemble the robot, and also a component bank where you have all the components currently available to build your current robots. Okay. So what takes the most time here to build the robot is 3D printing, which take between 4 to 7 hours, depending on the size of the robot. Assembling the robot actually is quite fast. It can take 5-10 minutes. So you can count to build one robot a day, between half a day and a day, depending on the robot. So to speed up the printing, that's why we have two 3D printers to be able to parallelize the printing of robots if you want to evaluate several robots. And we use also low resolution printing with a large nozzle to speed up the printing, which is much faster than high resolution printing. So as you can imagine, to be able to reach this automatization, successful automatization of building a robot, it takes a lot of engineering and tweaking. You see different step of design of robots. So there is tweaking in the robot fabricator itself, but also in the design of the robots itself. So I won't go into details right now because it wasn't my part of the project, but you can refer to this publication we had last year called Practical Hour for Evolvable Robots, where you have all the details from the electronics to the mechanical, all the constraints you have when you try to build such a system. So now, how do we evolve these robots? So now we can build physically robots, we can simulate them. So how did we optimize them? So as presented by Gus just before, we are using something I call morphoevolution with learning, where we jointly optimize the design, the body plan of the robot, but also its controllers, which is in our case a neural network. And we use a hierarchical optimization process or algorithm where you have two nested optimization process, an outer loop, which is an evolution algorithm used to optimize the body plan. And for each of these body plan, we use a learning process or learning algorithm to optimize the parameter of the controller to finally have a robot solving a specific task. So here we have a robot solving a maze navigation task, for example. So for the evolution side, I will talk about how did we encode the robot, because this is probably the most important part in an evolutionary algorithm. So here we use a CPPN, which stands for Compositional Pattern Producing Network, which is a type of neural network to produce shape or images originally, and we used it to generate our robots. So how a CPPN works exactly? You have to imagine that our robot is in a 3D space where you have voxels. Each voxel has a coordinate, X, Y, Z, and a radius from the center of the matrix. And you will use, so this is the input of your CPPN. You will query the CPPN for each voxel, and the CPPN will output what kind of things you will put in your voxel. So the CPPN could say you have to put a piece of plastic, which corresponds of a bit of the skeleton. So SK here on the slide, whether a wheel or a sensor or a limb or a caster wheel. And we have a last output alpha, which is the orientation of the component, if this is a component. So once you have queried the CPPN for each voxels, you get a raw morphology. I call it a raw morphology because it's not manufacturable yet. You can't build it with a robot fabricator. So we need to run some manufacturability tests. That was one of the most interesting findings in this project, is that when you use the evolution algorithm to generate robotic design, you don't have the guarantee that you can build it actually with your system. So we need to run these tests. So we have mainly 3 tests, which are specific to our robot fabricator. We test for overhangs on the skeleton because overhangs doesn't work really well with 3D printers. Do we have colliding organs, components? We call them organs. So do we have colliding components? Because of course, 2 components who are colliding doesn't work really well in simulation or in reality. And do we have the access to the gripper? So if you, as you have seen on the video, the robotic arm access the main frame, the skeleton of the robot from above. So we need to test if this robotic arm can access the attach point of the component to be able to attach it. So if any of these tests is not passed, to be able to make, to modify the morphology to make it manufacturable, we use a repress system where we remove the problematic parts, so we remove the overhangs, we remove the component, one of the components which are colliding, and we remove the component which is not accessible. So this solution has advantages and disadvantages. Of course, one of the big advantages is very simple and computationally efficient, and this is quite important when you are simulated a lot of robots and generating a lot of robots. However, the big disadvantage is that it introduces an indirectness between the genotype and the phenotype. And this is something we are not used to in evolutionary algorithm. Evolutionary optimization is the fact that the phenotype doesn't correspond directly to the genotype. And this is problematic for the exploration. So here we use to optimize the CPPN itself. So we optimize the topology of the network and also the parameter. And we use a simplified version of NIT, neuroevolution with augmenting topology, where we remove the speciation. So one of the big feature of NIT is the speciation. So we remove this part. And we still have mutation and crossover. And you have an example of lineage over 3 generations of one of our robots here. Okay, so on the control learning side, so we use a Hellman network to control our robots. This is a small recurrent network. We choose this because the small control is fast to optimize, and because when you have to generate hundreds of robots, it can become very untractable if you have a heavy learning algorithm and you have to optimize it for a long time. But we wanted also something quite expressive in terms of behavior you can encode in your control. So we went for recurrent neural network because of the small memory you can have in it. For the learning algorithm, we proposed a modified version of CMIS called NIPES, which stands for Novelty-Based Increasing Population Evolution Strategy. This algorithm uses 2 objectives, a goal-based objective, which is simply the reward of the task you want to optimize, and novelty, which measure how much novel is your behavior comparing with the past behaviors. Also, it's adapted from the increasing population CMIS, where your algorithm can restart and increase its population to increase the exploration power if the algorithm fall into a local optima or a premature convergence, and this is detected by the stopping criteria to stop and restart your algorithm. So you can have more details about this algorithm in this publication from 2020. All right, so one thing we studied as well here, so one of the main components of our algorithm is a controller inheritance. So if you want to speed up the learning, your process, it's good to be able to leverage what have been learned in past generation for the new generation to come. But it's not as straightforward because, for example, here, so this is not an actual lineage, it's just an example. The big problem we have is here we have a fixed neural network. So we have a fixed structure of the topology, fixed topology of the neural network. And you can't pass directly the control from the parents to the offsprings if the offsprings have a different number of actuators or sensors, which means basically it doesn't have the same number of output or input in your neural network. So how do you basically pass this information, this learned knowledge from parents to offspring? So what we proposed here is an archive inheritance where we have an external archive where we stored all the best control find so far, optimized so far during the learning. And this is stored in a 3D matrix where the dimensions are the number of wheels, number of joints, and number of sensors, which characterize the type of robot you have. So we classify, if you want, the robot by type or family where they have the same kind of control. So in this case, when you have a new offspring coming and have to start its learning, if there is a controller available in this archive, which is already optimized, you can start the learning from this controller, okay? And speed up the learning. So a sample of the result we had on this algorithm, so using all the things I've presented before, and show that basically it works to do this archive inheritance. This is an exploration task. where the robots start from the middle and have to explore as much as possible the environment. So we tested on other tasks. You can see, look at the publication here. And we compare in the first, the top graph, the best fitness obtained in the population over the generation, in orange without the archive inheritance, in blue with the archive inheritance. And we can see that we obtain a better performance with the archive inheritance. And it works because actually starting from a controls from the archive inheritance, indeed increase the initial fitness, the initial performance you have when you are starting the learning. So this is the bottom graph where you have in blue and in orange the best initial fitness, one with the archive inheritance in blue and orange without, and in green with the archive inheritance, which is the average initial fitness, and in red without the archive inheritance. And we can see that significantly, most of the offsprings robots start always from a better fitness. So with the same budget of learning, you can reach actually a better fitness, and you also speed up the learning process. Okay, so to conclude this talk, I would like to show you some video of the robot we obtained, because when we are talking about robotics, it's nice to see what they're doing. So here we have a wall dodger, which basically was trying to explore the environment and start from the middle and then go around. We also had a beacon finder. So here we have the robot without the beacon. So the beacon emit infrared light, and the robot is able to detect it with the sensors. Okay, so to transfer this robot from simulation to reality, we had to do some adaptation sometime, and sometime they were transferring directly. So yeah, so is able to go towards, so here another morphology able to go towards a beacon as well. So here featuring some legs. So this video is speed up 2 times. And finally, we also add some walkers and crawlers. So I'm calling them walker or crawlers because sometimes they're just crawling around. So this robot have been trained to go on the corridor and to go towards the beacon. This robot have been trained to explore its environment as much as possible. Yeah, and this one as well, to explore the environment. I quite like this one. It's quite fascinating and soothing to look at. And finally, the last one, which we have like, what is interesting with this one is that our system were able to evolve symmetry where we didn't have any symmetry, any condition for symmetry, and is able to move quite well. So yeah, thank you for watching. And so yeah, I would like to thank the whole team which I've worked with for this project. You can look at our publication, and if you have any question, feel free to ask. Thank you.